Hi friends, let's continue with the next classic problem of process synchronization. It's a wonderful problem named Dining Philosophers problem. Here what we have, let's look at the setup first. We have 5 philosophers who are sitting at a round table. Each philosopher alternates between thinking and eating, sometime thinking, sometime eating. So alternately thinking and eating. The philosopher means there is no timing restrictions for them, how long they think, how long they eat. So this thinking and eating periods are random for each philosopher. Don't know each philosopher how long will think, how long will eat, and all that. So between the two philosophers there is one chopstick. Between the two philosophers we have a chopstick, so totally 5 chopsticks are there, and that's how it looks like. There is a round table, we have 5 philosophers sitting around the round table. Before each there is one plate and we have a bowl of rice. So the plates are served with rice, and between two philosophers there is one chopstick. So in all there are 5 chopsticks, and to eat any philosopher will require 2 chopsticks so that can eat. So they need both right as well as left chopsticks. So the problem here is each philosopher first picks up the left chopstick available. If it is available, that means philosopher was thinking randomly for some time. Then when that philosopher wishes to eat, just forwards the left hand, looks for a chopstick. If the philosopher gets a left chopstick, then the right hand is pushed forward looking for the right chopstick. If it is available, the right one is picked. So when both are picked, now the philosopher eats for some time. How much time? Don't know. Then puts both the chopsticks back and then thinks for some more random time, and this alternates thinking, eating, and so on. So the another question is, why are we discussing about this philosopher and all that? How it is important in our current scenario is we are talking about process management. Under this we are talking about resource management, we are talking about process management, we are talking about resource sharing, and also we are talking about race condition to be avoided. That means any shared resource at most can be used by one process. So that's what is shown here. So to do a process like eating, a philosopher requires both the chopsticks, and if the process philosopher gets both the chopsticks, then continues to eat. So it is similar to our process wanting to get into critical section. So if it wants to get into critical section, then it should have all the resources available so that it can get into critical section. And we don't know how long it will be in the critical section, and then we don't know how long it will be in the non-critical section. So analogy, if we try to put between these two, is thinking is similar to a situation where shared resources are not required. That means non-critical state, and then eating requires both the chopsticks, so that means it is getting into critical state. A philosopher is a process, and if a process wants to enter the critical section, both chopsticks are required, and if gets both chopsticks, only then gets into critical section. And philosopher is used because the thinking and eating don't have any timing restrictions for any philosopher. That's first thing. Second thing is philosophers, if they are deep in thinking state, they don't bother what is around them, don't have any idea what is going around them, how many are sitting on the table, how many are eating currently, and all that. No, nothing they are aware of. Whether a chopstick is available or not, nothing they have a knowledge about. Only thing is, whenever they wish to eat, they just forward their left hand to look for the left chopstick. If they get it, then forward their right hand, and there if they get a chopstick, then they start eating. If they don't get it, then they wait for the chopstick to be available. So as simple as that. So that is what the dining philosopher's problem is, that is directly connected to our process synchronization. So the potential issues to solve here the deadlock. So it may happen that any given time one philosopher wants to eat, then looks for a left chopstick, gets it, then looks for right, gets it, eats it, leaves it, no issue. But what if all the five philosophers the same instant thought of eating? What if all the five philosophers thought of eating at the same instant? Then at the same instant all the five rush their hand, that is the left hand, forward and get one chopstick which was there on their left side, and then look for the second chopstick which is they want from the right side. And any philosopher, if you talk of, the left chopstick is taken by one, and the right one has already been taken by the philosopher sitting to that philosopher's right side, because the right chopstick of this philosopher happens to be the left chopstick of the right person. Therefore at that time all five chopsticks have gone into five left hands of the five philosophers, and therefore nothing is available on the table, and they keep waiting for someone to release the other chopstick they are waiting for, which is there on the left right side they want. Each one is waiting to get the second chopstick, and none of them is ready to release the chopsticks. Therefore we get into a situation where it ends into a deadlock condition, and they will keep waiting for the right one forever. So that is one problem we have. And then that is next thing is starvation. It may so happen that one philosopher may never get both chopsticks. So if others keep eating, then it may happen that that philosopher will be under starvation forever. Concurrency is the other issue, where multiple philosophers must coordinate without conflict. So if you want to make sure that everyone eats it, then some coordination is required. Why the problem is important? So this models the real world situations like threads sharing limited resources, CPU scheduling with semaphores, and so on. And most important, avoiding deadlocks and starvations. So what is happening here is in a algorithmic language, if we want to represent this situation, then the process is in the thinking state for some time, that is working in a non-critical section, then wants to eat. So before eating, now wait for the left chopstick. If you get the left chopstick, then wait for the right chopstick. If you get right also, then eat, and then place the two chopsticks back onto the table, and this repeats. Think, eat, alternately repeats. So how can we solve this problem? One problem is give a hierarchy to the resources, number the chopsticks, and make sure to pick the lower numbered chopstick first and then higher numbered. Then what happens is we have 5 philosophers, number them 1, 2, 3, 4, 5, and we have 5 chopsticks. If you number them starting with the left side of the first philosopher as 1, then the next one is 2, then 3, then 4, then 5. So that means, so the fifth philosopher left side is 5, right side is 1. So the fifth philosopher left side is 5, right side is 1. So let's look at again from the beginning. So philosophers are named round, counterclockwise if you say, then 1, 2, 3, 4, 5. The left of philosopher 1, if we call it 1, then the right of philosopher 1 will be 2, or the left of philosopher 2 will be 2, left of philosopher 3 will be 3, left of philosopher 4 will be 4, left of philosopher 5 will be 5, and back you will get 1 again. That means right of philosopher 1 is 2, right of philosopher 2 is 3, right of philosopher 3 is 4, right of philosopher 4 is 5, and right of philosopher 5 is 1. Round it. Now if we somehow make sure that if they want to, any philosopher wants to eat, then the lower number should be picked first and then higher number. Then philosopher 1, philosopher 2, philosopher 3, philosopher 4 have to choose the left one first, whereas philosopher 5 should choose right one first. If philosopher 1 has done it, then selected the left one, that means the chopstick with number 1. The same time, if philosopher 5 wants to use it, then 5 tries to select the smallest number. Smallest number is already 1, therefore it cannot get a 1. Since it cannot get 1, then it will not try to get 5. Therefore philosopher 5 will not pick any of the chopsticks. Now what happens? One of the remaining 4 will get both the chopsticks, and they can complete their job, place them, then another one may get a chance, place them back, another may get chance, because out of 5 only 4 can look for that. Fifth one is definitely not allowed to pick even one. So that is one condition for deadlock is have some resources and then wait for others. So the philosopher 5 will not have even one, therefore will the first condition that fails, and hence there won't be a deadlock. So this prevents the circular wait, and hence there cannot be any deadlock. Other solution is make sure that any given time maximum 4 should be eating at any given time, not all 5. So make sure that out of 5 only 4 will be allowed to eat. So allow only 4 philosophers to sit and eat any given time. Keep one place free. Though there are 5 chairs for 5 philosophers, make sure that one of the chairs is empty. So with that what happens? The number of philosophers 1 is less, and So there is always a chance to complete the cycle, and hence there won't be any deadlock. So this or allow a philosopher to pick up the chopstick only if both are available. That's another way. So take one, try for other one. If both are available, then continue in the critical section. If both are not available, place whatever you have taken back. So look for one, got it. Look for second one, did not get the first one, keep it back. Wait randomly for some time and try again. So may be possible that other two are available say in the same time. So that's another way to solve the problem. One more way is asymmetric solution, where the odd philosophers pick first left then right, and the even philosophers pick right and then left. Don't make all the time all of them to first pick left and then right. So we can make odd people work left and right, and even philosophers can do right and left. In this, what happens is, if philosopher 1 first picks up the left and then goes for the right, and whereas the philosopher number 2 is not looking for left, but he is looking for the right first. So he may get the right first, but the left one is left as it is, which the philosopher 1 may grab it. So that way philosopher 1 will get both the chopsticks, continue to eat. So that way another possibility. So this breaks the symmetry and hence avoids the deadlock. Or use a semaphore. So make maximum concurrent eaters to be 4. So don't allow more than 4 to participate in eating any given time. So any time each philosopher must wait for the butler before picking the chopstick. So 4 butlers you keep, and make sure that if you get the butler, then go for picking the chopstick. That means make sure that maximum 4 of the philosophers can eat it. So instead of having 5 plates, keep only 4 plates. So the 4 philosophers will get 4 plates, and if they get a plate, then look for the chopstick. Only 4 will get the plates, then one will not get the plate, so one will not participate in picking the chopstick. So this way the round waiting is avoided, hence deadlock is prevented. So that's one wonderful way of explaining how to prevent deadlock when we come across with this. The major reason for using this problem is the behavior of the philosopher. They are deeply involved in thinking so much that they forget what is around them. That means our processes do not have any idea about how many other processes are currently running in the system. Second, we don't have, no philosopher has any idea about what is happening with the chopsticks they want. That means no process has any idea about which resource is being used by whom at any given time. And still, if you want to make sure that the whole process should keep running without getting into deadlock, then somehow ensure that each philosopher somehow keeps eating, not starving at all. So that's a wonderful example we had to explain the logic of how to manage the process synchronization problem and how to avoid deadlock, how to keep the whole work going without halting, without getting into deadlock, without starvation and all that. Hope you enjoyed this journey. So make sure to like, share your comments, share with your friends, and do subscribe to this channel, and keep commenting what else you want from us. So that's it for now. Thank you.